In this video, we'll look even closer at normally distributed variables and see some of the limitations of the empirical rule when it comes to finding probabilities for normally distributed variables. We will revisit the concept of a z-score and see how z-scores allow us to go beyond the empirical rule. Hopefully, one of the concepts that the previous examples made clear is that the total area under the normal curve is 1 or 100%, and that the area under a specific portion of the curve represents the probability that the variable will fall within that range. So the total area is 1 or 100%. This is split evenly into 50% chance that the variable will be lower than the mean and a 50% chance that it will fall above the mean. Once we go beyond 3 standard deviations from the mean, the area is essentially 0, meaning that it is very unlikely an observation will be more than 3 standard deviations from the mean. What distinguishes one normal curve from another is 2 things: the mean and the standard deviation. This graph displays 3 normal curves. They all have a mean of 50, but one has a small standard deviation, namely 5, and is tightly clustered around the mean. The other has a standard deviation of 10 and is more spread out, and the one with a standard deviation of 16 is very spread out. Conversely, this graph shows 3 normal curves. Here they all have a standard deviation of 5, but have different means, so they are located at different centers. It is important to realize that if you change the mean or the standard deviation, you change the location and the spread of the graph. It still stays bell-shaped and has the percents as given by the empirical rule. The intent of this matching is to get you comfortable with the notion that the area under the curve corresponds to the proportion of cases falling in that range. The pulse rates of women are normally distributed with a mean of 76 and a standard deviation of 8. Which graph represents the proportion of women with a pulse rate greater than 86? Well, the mean is 76, and it appears at the center, and 86 exceeds 76, and greater than would be shading above, so it must be graph B. What about less than 66? Well, 66 is less than the mean of 76. And less than means below, so it must be graph A. So what does graph C represent? The boundary value is the same as B. That would be 86. So it is interpreted as the proportion of women who have a pulse rate of less than 86. Another one. This time, it's the number of hours of sleep that college students get. It's normally distributed with a mean of 7 hours and a standard deviation of 1.7 hours. Which graph represents the proportion that get less than 7 hours of sleep? Well, 7 is the mean, which is located in the center, and less than means below, so it must be graph C. Between 5 and 9, well, 5 is less than 7, and 9 is greater than 7, and between means in the middle, so it must be graph A. And graph B is shading above 7, so it would be the proportion of college students who get more than 7 hours of sleep at night. Back to the concept of a z-score that was first introduced in the beginning of the chapter. You may recall both the formula and the interpretation of a z-score. It measures how many standard deviations from the mean an observation is. If we're a whole number of standard deviations from the mean, say 1 or 2 or 3 standard deviations, then we can rely on the empirical rule to help us find probabilities. If, however, as we'll see in our next example, our z-score is not a whole number, we'll have to use another process. Here we are told that pulse rates for women in their 20s are normally distributed with a mean of 76 and a standard deviation of 8. What is the standardized, or z-score, for a woman with a pulse rate of 88, and interpret this z-score? The calculation is straightforward. We calculate z as 88, that's the x value, minus 76, which is the mean, divided by 8, which is the standard deviation, and we get a z-score of 1.5. This means that the woman in question has a pulse rate that is 1.5 standard deviations above the mean. Now, when we calculate z-scores based on a normally distributed variable like pulse rates in the last example, all we are doing is creating a new normal variable, namely the z-scores. It turns out that z-scores have a mean of 1 and a mean of 0 and a standard deviation of 1. This special normal distribution with a mean of 0 and a standard deviation is so important that we give it a special name and call it the standard normal distribution. Here is a picture of the standard normal distribution. Notice how it is centered at 0, and because the standard deviation is 1, almost all z-scores are between plus and minus 3. So once again, the units marked on the horizontal scale of the previous slide are the z-scores, and what a z-score tells us is how many standard deviations above or below the mean a particular observation is. Here are 3 questions to test your understanding. On the standard normal curve, what percent of the observations are between -1 and 1? Hopefully, you will respond 68%. Between -2 and 2. Hopefully, you'll respond 95%. And finally, between -3 and 3, hopefully, you'll respond 99.7%. So let's return to the woman with a pulse rate of 88 who had a z-score of 1.5. We cannot use the empirical rule to find the proportion of women with a pulse rate in excess of 88 because it is not a whole number of standard deviations from the mean. It is 1.5 standard deviations from the mean. So we will use a whole different process. After converting 88 to a z-score of 1.5, we will use an online calculator to find the area above a z-score of 1.5. The calculator, which will be described momentarily, will tell us that the area above 1.5 is 0.0668. So we can then report that 6.68% of college women have a pulse rate that exceeds 88.